Welcome to the course on FPGA based signal processing systems. We are doing this infinite impulse response filter. Some of the designs we had learned, that is impulse invariant method and bilinear transform, how to discretize the analog filter into the discrete domain, or designing the digital filter. In that process, first we need to design the analog filter. The examples which we have taken here is that Butterworth and Chebyshev. There are other types as well. Just show you that how the analog filters can be designed, and then using that analog filter transfer function, then we can discretize it using the either or discretization procedures like the impulse invariant and the bilinear transform. Today we look at some of the examples along with this Butterworth and Chebyshev filters and its characteristics. So Butterworth filter, which is having the characteristic which is shown over here, in which that the magnitude or response of for n, the order n 1 2 4 and 10. So you can see the blue line which is n and 1, n equal to 1, n 2 3 4 and 10. So the cutoff frequency is marked over here, and it's plotted with respect to omega. So when we see this characteristics, the pass band which is over here, it exhibits maximally flat response in the Butterworth filter, and the stop band is monotonically decreasing. As the order increases, you can see the better and better cutoff or the attenuation. So this characteristics, the order of 10 gives the sharper cutoff compared to order 1. The equation obeyed by this Butterworth filter is that 1 by root of 1 plus omega by omega c power 2n. So n is the order here, omega c is the cutoff frequency. So this particular expression, if you plot it with plot omega with respect for h of j omega with respect to omega, then you would get this functions. So there is no ripple content, and ideally here the maximally flat response and the monotonically decreasing response of the stop bands. So when we get this h of j omega magnitude square, so h of j omega conjugate of h of j omega, which would result in h of j omega and h of minus j omega. So if you look at this transfer function in the s plane, h of s and h of minus s is equal to j omega over here, 1 by 1 plus this omega where we had in the previous slide, it is omega replaced with s, and so j by omega also that is becoming j omega c over here. So from this this is the one here. If we want to express it in terms of s, then yes, j omega would be multiplied by j in the numerator and denominator over here in this function, then you get s, and here j omega c power 2n. So how do we get it? This is converted into the s plane to see the pole locations of the analog filter. So the hi of s, if you take only this analog transfer function, I have to mention it here, this is same as h of s, omega c per n, it has poles, the product of omega c per n by product of k is varying from 1 to n, s minus pk. So the poles are over here. So we can have this to find the pole locations exactly, s power 2n. So this one, if you cross multiply and equate it to 0, the denominator minus j omega c power 2n. So in this j omega c power 2n, it can be taken over here, the minus 1 part, which gives the e power j by 2k minus 1. So minus 1 can be written in this fashion with 2 power n part, which can give n number of poles, and that would be the mirror image in hi of minus s as well. So if you compute that whole thing here, the minus 1 j omega c 2n, so which is simplified to this functions e power j by 2k minus 1. So if you take this one, we can say this can be written as cos pi into 2k minus 1 plus j sine pi into 2k minus 1. So the where k varying from here 1 to 2n, so that can be dealt in the location. So from this cos pi and plus j sine pi, just giving the minus 1 here at various locations of k, where k equal to 1 it becomes pi here, at k equal to 2 this becomes the 4 minus 1, this is 3 pi, and then if it is going to be 3, then 6 minus 1 5 pi, 5 3 pi, 5 pi, and so on. So we have this one, it exhibits minus 1 the value. So the pole location pk can be j omega c, in this is j omega c into e power j pi, and this 2n is over taken here, that is minus 1 power, the whole thing power 2n. So that is going to be 2n into 2k minus 1. So k varying from 1 to 2n gives us the pole locations of the Butterworth filter, in which we have the pole locations where the radius of the circle which forms in the S plane is omega c. So you can see that location. So this is here, so marked as omega c over here, or we can have the radius of this is omega c, and you can see the pole locations 4, and we can have this n order as 4, and here also n order 5, okay, 4 and 5. So which h of s, this is minus s and this is h of s. So here is the left side and this is the right side, RHS of RHS and left LHS of the S plane. These are the poles could be identified from this expression, or we can calculate it. You can see this omega c, which is the radius of that. Also similarly for k equal to 5, this becomes the picture 1 2 3 4 5 poles in the h of s and 5 poles in the h of minus s. So the radius is seen to be omega c. So in the normalized all the poles, if we compute all the poles and multiply them with the omega c is a part of that. When we take omega c equal to 1 and normalize the equation, the denominator polynomial of this Butterworth filter, that would result in for the order 2, order 3, order 4, 5, 6, 7, 8 in all this thing. So that you'll get the expression of these coefficients here, normalized coefficients a n minus 1. If it is n equal to 2, this will be a1 only here. It is 2s square plus a1s plus 1. So that would be the equation of the normalized Butterworth polynomial, and which gives the pole location. So this table gives the different order and the coefficients. So once we know the order of the filter which we are going to design according to the specification, then it's easy to pick up this or the polynomial which is fixed for the order, and the omega c can be incorporated in that to get the actual pole location of this. Instead of having the unit circle, if omega c is 1, then we need to have this cutoff difference on the cutoff frequency, that needs order should be picked up, and the cutoff frequency depends on the cutoff frequency. The polynomial pole locations, from the polynomial pole locations can be identified. That decides the filter characteristics here. So with this, how the design we would like to proceed. So normalized Butterworth filter which has omega c equal to 1, that is a 1. If we have this, the HI of s, this is given the analog filter, so specifying this h suffix a, which is same as h of s we have discussed in the previous 1 by s power n a n minus 1, and this is the normalized polynomial which we will be getting. So in this, what are the steps to be followed in the design? So we have to find the selectivity factor k and the discrimination factor d. There are two things involved in the design. What are these k and dr? Okay, so the selectivity and discrimination factor, and then we go for the order of the filter by knowing this d and k. So log d by log k, that is n is great at least log d by log k, which is from the k and d. K and d are related with the ripples which are allowed in the pass band and the stop band here, or the attenuation. We can say what are the attenuation we need in the stop band. So set the 3 dB cutoff frequency from after finding the order. So omega p is the pass band frequency and omega s is the stop band frequency. So if we know that omega p and omega s, del p is the ripple allowed in the pass band and del s is the stop band one. In that case, it is omega c, the cutoff frequency can be fixed between this omega p and omega s. Okay. So after knowing this 3, once omega c is fixed, then that the expression using this, using the HA of S and HA of minus S can be obtained 1 by S plus j omega c to n. So the HI of S alone, from that we can get the poles, so that the right half S plane poles will be the mirror image. Here as HI of S is that what we had, 1 is varying from here, k is varying from 1 to n, S minus pk. So from this, the pole location or what we had calculated in that can be identified. So if we vary k equal up to 2n, you will get all the poles. If order is 3, then it would be 6. There will be 6 poles you will be obtaining, but 7, and you will be having the poles of 14 in the S plane. So this is the design procedure, and then we can have this one. Similarly for the Chebyshev also, Chebyshev filter which has the normalized polynomials, and the allowed ripple in that is 1 dB ripple or 0.1 dB ripple or the 0.2 dB ripple, and so on. So if the ripple is specified in the case of, this is related to the Chebyshev, and the coefficients also differ in the Chebyshev filter. So this table is giving the Chebyshev information. Like the Butterworth, we can have this Chebyshev also have them. Once know the order, then we can pick the coefficients for the ripple specified 1 dB ripple, or if this is 0.1 dB ripple, the table is completely different, and from the 0.5 dB ripple, so what is allowed in the pass band and stop band. So what is the variation in this in the normalized Chebyshev polynomial? We look at the what are the type of filters actually when we do the Chebyshev like. So the Butterworth filter example, if you take design a low pass Butterworth filter to meet the following specifications. So FP is given as 6 kilohertz and FS is 10 kilohertz. So del P and del S, the ripples allowed is 0.1 here, that is we have the pass band and stop band frequencies 6 and 10. So definitely the FC would be in between these two. Okay, the first find the discrimination factor D, which is the, here we have 1 by, the expression is, it's quite little looking complicated, but not so. 1 by 1 minus del P whole square minus 1 by 1 by del S whole square minus 1 half. So this is giving the del P is the pass band ripple, del S is the stop band ripple. So anyway, the 1 minus del P is the if the maximum is 1 or 0 dB, then how much ripple allowed in this, it's del P specified as from the magnitude response. So 1 by del S the whole square minus 1 D is D for the given del P and del S, we get this 0.0487. So similarly, the K, the selectivity factor, which is depending on the pass band and stop band frequencies, so Fp by Fs, which is equal to 0.6. So over here Fs is 10 and this is 6, so you get the 0.6 as the factor, selectivity factor. So once we know that these two parameters, then order can be specified. N is at least greater than or equal to log 2 by log k, which is 5.92. So this is the order 5.92, the order should be integer. So we closely take the value which is going to be the round off of n equal to 6. So to meet the particular specification for the given allowed here, and the 6 and 10, which is n equal to 6. Anyway, so it will be maximally flat response. That maximally flat response, how through the design we need to achieve that the allowed ripple is given as 0.1. So it's the width, the oscillation in the magnitude response in the pass band and in the stop band is minimum, it should be 0.1. So once we know the pass band and stop band characteristics, and then stop band frequency and the pass band frequency, so it will be easy to decide the order n equal to 6 using the discrimination and the selectivity factor. So from we know that to select cutoff frequency, so omega p into the minus 1 by 2n, which is lying the next step between these two. So if we call del p and del s, fp fs is known, so that should be cutoff frequency should be between any of this 6819 to 6770. So we can choose 68000 as well. So that would be the cutoff frequency of the filter for this particular order, n equal to 6. So that's just deciding the order and the cutoff frequency. Once we know the order and the cutoff frequency, we can get in the pole location formula. If we substitute that, and then we get the pole locations of the filter, and the pole locations, if you multiply this all the poles and get the transfer function of the analog filter. Once we have this transfer function, then go for the discretization process for IIR filter, either impulse invariant or bilinear. So bilinear transform would be the better than this impulse invariant, so that can be done. So once discretized, and then get the coefficients and develop the Verilog module, as we had seen in one of the examples of the how to write. Once we have these coefficients B naught and A naught, that is feed forward and feedback coefficients, the Verilog module can be developed. So for the next one here, determine the order and poles of the low pass Butterworth filter, which is having the minus 3 dB, bandwidth 500 hertz, and attenuation of 40 dB at 1000 hertz. So in this case, minus 3 dB bandwidth, so which is the cutoff frequency, giving that 500 into 2 pi 1000. So next omega s is again 1000 hertz, which is 2000 pi. So attenuation is given 40 dB. So 20 log del s, that is the stop band ripple, is minus 40. So del s comes out to be 0.01. At least it needs the attenuation at this point is 40 dB. So the magnitude square, which is given as is that at the if you calculate that from the magnitude response 1 by 1 plus omega c whole power 2n, this is square. So the root is taken off when you square it, and then what is the value of this omega required at 2 pi 1000? That is what is given over here in the specification, which is at 1000 hertz it is going to be 40 dB. So for this 40, so if we substitute over here, omega is 2 pi 1000 and omega c is known, which is 2 pi 500, that is 500 hertz. So you get 1 plus 2 power 2n. So from this you equate this to be 40 dB requirement, that is del s, it's going to be del s, this is square, which is 0.0001. So calculate the n base, adjust the base here, 2 power 2n is this, and 2n log base 2, which is going to be this, and n comes out to be 7. So if we calculate from here, that is, this is calculated, the order of the filter is calculated from the magnitude response, which is given at that particular frequency. What should be the magnitude response? So you need to meet that specification instead of having the finding the discrimination factor using the del p and having that expression d and k, that also relates to the order of the filter. Here the specification is doesn't mention any of this passband ripple. Okay, so instead of that, order can be found from the magnitude response, which needs to be 40 dB attenuation at a certain frequency. So we use that expression and then a specification and find the order. So once we have this order n equal to 7, so using the pole location j omega c, j pi 2 k minus 1, so substitute them. Omega c is 1000 pi, that is the cutoff frequency, and then I have this n equal to 7. Okay, so substituting them, we'll get here, and the k equal to 0 to 2 n, you'll get 14 poles. So you can see the poles, which this is multiplied with 1000. Okay, all these poles of magnitude, the amplitude is different, so it is multiplied, the common taken 1000 into all these values. So minus 0.6991, this is one pole, and this second pole, you can see third pole, fourth pole, and so 5 6 1 2 3 4 5 6 7 up to 14 poles are here. So you can see the poles which are in the mirror image of minus 0.6991, and this is here plus 0.8. So the real part is 1. This is in the left half of the S plane and this is at the right half of the S plane. Okay, and its conjugate also you could find here, minus 0.66. Here is a conjugate of this. Okay, and you can also find the conjugate of this. Okay, so you can see the circle forming through this folds on the S plane. The 1.899 similarly will have this replica 1.8985 here also, that is a mirror, and the conjugate of this can be mirror and its conjugate can be 1, 2, 3, 4 poles are there. So these two are conjugates, these two are conjugates here. So these are the pole locations of the filter which has the characteristic of Butterworth. So this exhibits maximally flat response and the monotonically decreasing response in the stop band, but the allowed ripple which is small over here. This is one design of the Butterworth filter. After getting the I mean S minus, making all these poles, multiply all the poles and you will have this polynomial or the denominator of the hi of s. So 1 by that would give the hi of s, and then after that you can discretize it. So considering the Chebyshev filter, the response, that's about the Butterworth and the Chebyshev, how there are two types of Chebyshev and type 1 and type 2 Chebyshev filters. It follows the Chebyshev polynomials. Give the little bit insight about this Chebyshev and then if you go do the design. So here the characteristics, this is type 1 Chebyshev with the omega versus HA of j omega. If you plot them, okay, so the characteristics gives this, there is a ripple in the pass band and the monotonically decreasing response in the stop band, which is also sharper. So you can see this is, if omega c is 1, then this is going to be, this is normalized response. HA of j omega magnitude 1 and epsilon is defining this ripple over here, 1 by root of 1 plus epsilon square. So here similarly you can see the same type 1 filter, which in the pass band there is a difference here, the ripple starts over here at the bottom or the ripple starts over here. Okay, so it depends on that n equal to 6 here and n equal to 7. So n even order, all even orders, the ripple starts, the Chebyshev polynomial thing is because of that it starts over here, and for the odd you can identify the from the characteristics, this is odd number or even order. So it starts from here, n equal to 7. So you can see that crossings as well. So here 6, 1, 2, 3, 4, 5, 6, 7 here. So it would serve 7. The starting point would also give the details of this magnitude response. So with this, what is the equation obeyed by this? H of j omega or h of j omega, we use this both the notations. H of j omega equal to 1 by root of epsilon square Tn square omega by omega p. So Tn is it's a function, it's a Chebyshev form, this polynomial. Omega by omega p is this is actually the one function, Tn square omega by omega p the whole square. N represents the order here. So let's look at this characters poles locations of this n equal to 7. So right half, this exhibits elliptical characteristics, elliptical pole location. The characteristics, the locations of the poles are placed on ellipse, not a circle. You can have the mirror, yes, like the Butterworth filter, not on a circle, but those are the elliptical pattern. You can see them in the S plane. This is in the S plane anyway. So this is real of S. Here is similarly real of S and imaginary of S. So this part is giving h of s and here h of minus s. So similarly here as well h of minus s. So the order 7 and order 8. So you will have the number of poles according to the order. So the design process, as we have done in this, find selectivity factor k and the discrimination factor d, which d is related to delta P and delta S, and K is related to the passband and stopband frequencies. From that, determine the order, where you can note down this is not log of d by log of k, that this is cos h inverse hyperbolic function 1 by d 1 by k. So this n can be obtained from this expression. After getting this k and d, find the order, and then go to the this system function, the equation hi of s in the s plane 1 by epsilon t n square s by j omega p. So it is j omega, so omega by omega p, it can be that s is equal to j omega. So epsilon is related to 1 by del p square minus 1 root. So the epsilon is here, okay, which is related to the one which is in the characteristics we have seen, 1 by 1 root of 1 plus epsilon square. So that, equating that to 1 or 1 minus del p, you get this expression. Here it depends on the even and odd order. So in type 1, as we had seen, I have shown this thing, the characteristics of type 1 filter. It is all pole and it is equiripple passband. The passband has a ripple which is equiripple and monotonically decreasing stop band response. So you did not see any ripple on the stop band. So like that, any equiripples on the stop band in type 1 for this is all pole filter. And then type 2 is just inverse of this. This is monotonic passband. So passband doesn't have any ripple characteristics, or it is going to be a maximally flat one like Butterworth, and an equiripple in this stop band. Stop band has the characteristics. So here if you see them, you will have the response in this. This is omega, and here this is type 2. So whereas type 1, the one is what we had seen already, that is, so which has a ripple over here and monotonic response in the stop band. So that's a difference. So it depends on that the equations would also, the specifications and other things would vary. So the Chebyshev polynomials, little insight on the Chebyshev polynomials. So Tn of x, that what is used in the Chebyshev filter, is cos n cos inverse x. So this is the cos of x, which has this x has this cos inverse, where for x is less than or equal to 1. If that is x is greater than 1, it exhibits cos h n cos h inverse x. So if you plot it, we can get this polynomial. So here the recursive equation in the polynomial is k plus 1 x equal to x 2x kx minus k minus 1x. K is greater than 1 or equal to 1 here, then we can use this expression to find the order. N can be that. So T0 of x is equal to 1 always, and T1 of x equal to x. So if this is 0, initially this is equal, this expression, this starts with 1, and then it is equal to x itself. So x is the T1 bx. So using that, we can have the polynomials generated. Once have this Chebyshev polynomial, that can be the denominator polynomial of the Chebyshev filter. So if you know the order, which can be identified, and x can be decided from the omega passband frequency. So when we compare these two filters, that Chebyshev filter has a sharper cutoff, we have seen in the type 1 filter characteristic, which is smaller transition band than in the Butterworth filter. Butterworth filter, which has, as the order increases, the stop band is better and better in that case, whereas Chebyshev filter have the sharper cutoff, and which is done with the passband ripple. So the Butterworth has the maximally flat response, that's good, and the passband. But whereas here the Chebyshev exhibits ripple in the passband in the type 1 case. Of course, the rippling in the stop band is allowed. In the case of type 2, would be better comparison in that case. So if we have this Chebyshev filter, which is, if we take the same specification, order required for Chebyshev filter is less compared to the Butterworth to meet the same specification. So in that case, n order, the order, if order is less, that is good to have the same better response. If order is less, that would be preferable. So for the same specification, is that Chebyshev gives the lower order filter. So if we take the example of the Chebyshev design with D and K are given sum, the discrimination factor and the selectivity factor. So you can easily decide n from that. So cos h inverse from the steps of the Chebyshev filter design, 1 by d by 1 by k, so which is coming to be 3.38. So you can see that 0.04, 0.6, which is less than here, the n equal to 4 when compared to the Butterworth for same case. Okay, so n equal to 4 in this case. That was 6. So epsilon you can find that is related to the pass band, which is giving 0.4843 from the expression 1 by del p square minus 1 root. So if we have this epsilon in the expression of the Chebyshev filter, we can substitute over here. And how do we find this function, that Chebyshev polynomial, which is the denominator polynomial of the filter? So here t and x, so n we get is 4. So the recursive equation T4 of x otherwise, so here equal to 4x cube minus 4x. So what is x over here? X is this portion, omega by omega p. So if you substitute x as omega by omega p and get the expression in terms of omega by omega p instead of x, that is the and square it, that would be the polynomial expression, which is, and multiply this with the epsilon square, which is got 0.4843, and root, give the magnitude response. So you can have this magnitude square response is 1 plus epsilon square and into this function Tn square. So x can be obtained from the omega is actually the variation, and omega p is known, which is from the here we got it from the specification omega p. So we can get this expression and get the HI of s completely, and HI of s from that pole location also can be identified. You can see them as this is forming the elliptical fashion of the locations. So coming to the with this background of Butterworth and the Chebyshev filters, we'll be designing one example with the impulse invariance and then the bilinear transform also. So taking that HA of s or the continuous transform HC of s. Okay, so H of s or HC of s, HA of s does mean the same, equal to omega c by s plus omega c. So this is the cutoff frequency given. 3 dB cutoff frequency is 10 per 5 radians per second for the first order. So in that, what is the procedure in the case of impulse invariant method? We had listed in the previous lectures. So take the inverse Laplace transform, that is Hc of t equal to omega c e power minus this omega c t u of t. So this is for the pole e power minus alpha t, or if 1 by s plus e alpha, that is going to be e power minus, you can take the transform Laplace transform pair for it directly, omega c e power minus omega c t into u of t. So with this continuous time function Hc of t, the impulse response of this, then we have to discretize it now. So n h of n is, we can call this h of n, this is n ts actually, n t is replaced with n ts, so we get, so omega c, so let's hold this ts for some time, Hc of n ts equal to, you can see omega c, this particular thing omega c, and where t is, this t is replaced with nts, minus omega c nts, and this t is replaced with 1ts. And in the step we have also provided ts needs to be multiplied with the h of n. Okay, so that is the thing, the step which we had done here, the ts needs multiplied, h of n, ts multiplied, drop this for clarity, h this ts, h of n here, hc, this hc of n, this is n, and ts omega c e power minus omega c, and here ts power n, so it is given as power of it. Okay, this n u of n. Okay, so this is taken as common. Okay, and then if we take the z transform of it, once we have this h of n function, that means sample the impulse response, the continuous time response is now sampled and multiply with ts. Okay, so this is the function h of n. Now taking to get the transfer function of this filter, we have to discretize, get the z transform of it. So Z transform, Ts is common here, omega c is also a constant, we can take them out in the summation. N is varying from 0 to infinity here because it's the first signal is u of n, that's a step signal which exists from 0 to infinity, and the function needs to be, this is x of n, or the for which that Z transform to be taken, e power minus omega c Ts and Z power n, actually this is omega c Ts power n into Z power minus n, that's equation, right? N equal to 0 to infinity. So that is this is simplified form. Omega c Ts is minus 1 whole power n. So from this, what is the this, if this is a power n, summation n is varying from 0 to infinity, a power n, it's equal to 1 by 1 minus a. The closed form solution of this is. So here we have T is omega c and a is 1 by 1 minus a, we have taken, this is a. Okay, so we got this expression as the Z transform for the impulse response. So this is the transfer function. We substitute omega c Ts, and Ts needs to be decided in this. Omega c is given. Okay, so it doesn't specify any sampling frequency here, or the specification itself will give the Ts. So taking this into consideration, we have the magnitude response from the analog filter omega c omega square omega c square root, that is substituting s is equal to j omega. So approximating it give you that is considering omega is far greater than this omega c, then that is omega, this expression reduces to omega c by omega. So this expression holds true if we'll take that drop of 10% drop from the in the magnitude, so that so this omega is j omega is pi by t. Okay, so substituting that pi by t Ts here, approximated to omega c by omega, omega is pi by Ts, take this 10, this magnitude response to 0.1. So it would be the 1% drop of the magnitude or 10% drop of the magnitude can be used for designing the filter for computing or fixing Ts. So pi by T is equal to 10 omega c, which is resulting 10 power 6. So T is equal to 10 power minus 6 into pi here. So this is the sampling frequency. Once we know the sampling frequency, we'll substitute over here in the previous case Ts in the transfer function, which results in h of z equal to 0.3142 z by z minus 0.734. We have the transfer function now, the discretized version using impulse invariance. So impulse invariance steps have been followed, that get the inverse Laplace transform and then multiply by Ts, sample it and then multiply by Ts, and then get the h of n and then take the Z transform. So if you want the equation of this in the time domain again, so we can go for inverse Z and get the equation for the structure, to get the equation of the structure of the filter. So here small piece of MATLAB code also specified over here. T is this Ts, what is specified, pi by 10 power 6 or 10 power minus 6 into pi. This is what the T is, and Fs sampling frequency is 1 by T. So numerator of the filter, that is omega c, so 0, the first coefficient is 0, and numerator polynomial 0 and 10 power 5. Denominator is has s plus omega c, so 1 coefficient 1 and 10 power 5. So using this get the impulse invariant is the built-in function in the MATLAB. So numerator, denominator, comma and Fs, give that and you get the coefficients, this particular a and b, the numerator polynomial and denominator polynomial can be obtained. So which gives 0.3142 also, and 1 and minus 0.7304. So after getting this expression, transfer function for that filter, discrete one, and y of n, now we take the inverse of y of n, cross multiply and take the inverse, so 0.734 y of n minus 1 plus 0.314 txn. So this is the, so we will do the structure for it, and x of n into 0.3142, which is b naught alone, and then y of n multiplied and then delayed. This can be delayed and multiplied as well, 0.7304, and add it, get the y of n. So this is the structure, and we know the b naught, one coefficient, and a1 another coefficient. So with this, we can have the Verilog module also. So the small modules can be generated for this to get the filter response. And is the same problem if we do it with the bilinear transform. So look, we can see that how only the fixing of Ts is will follow the same way as the previous case. Otherwise, this omega c by s plus omega c, what is the transform used? S equal to 2 by Ts 1 minus e power minus 1, the bilinear transform from that, directly substituting here. Yes, and 10% drop of for the Ts, the same explanation we have repeated here. 0.1, when the magnitude drops to 10%, taking that into that point and find the Ts at that point by substituting this omega c. So this sample is equal to 10 power 6. So here is Ts is 10 power minus 6 by pi. So the h of z from this, so we have straight away substituting this s, so we can get the expression of z, expression in terms of z, h of z equal to 0.1358 z plus 1 by z minus 0.7285. So this is the transfer function in z obtained. So from that we can also get the inverse c. So just simply s is replaced with the bilinear transform expression. So we get 0.7285 and 0.1358 and 0.315158 here for x of n and x of n minus 1, both the cases. So if we draw the structure from it, x of n 0.1358, 0.1358 and 0.7285 the delayed. So these are the two coefficients over here, b0 and b1, b0 and b1, and this is a1 here, 0.7285. The structure would look like this. So we can go for the Verilog module to generate this characteristics, and the piece of code of MATLAB gives t, same Ts we have fixed, and Fs, numerator 0 and 10 power 5, and denominator also. You can get the numerator polynomial and denominator polynomial from this discretized version. Is the bilinear, is a built-in function like impulse invariant. Numerator denominator Fs, get s plus 1 is at minus 0.27, 0.7285. So once we have this analog filter expression, then discretization can be done this way, and we can design this analog filter also using the software if the order increase and the things. So the FTA tool can be used to design this IR filters with this bilinear transform or the impulse invariant, Chebyshev type 1 or type 2, all of them. So from this we have learned the design procedure of the filters, the analog filters, listed out the steps involved in the design. So still we have maybe we didn't refer the table which is used, so that can be done in the tutorials as well. So Butterworth filter, Chebyshev filter, design steps, and how to find the order and how to find the pole location, how to get the transfer function. Once we got the transfer function of these filters according to the specification, then discretization process will give you the digital IR filters. So once we have the coefficient in the digital filter of the digital filters, that could be used in the Verilog module, and for testing the characteristics, the filter will get into the FPGA. So the design process will be outside the FPGA to getting the coefficients for FIR and IIR both. After designing it, are getting the coefficient, then the filter can be realized in the FPGA, which to exhibit the characteristics, and the process of module simulation and then synthesis and then finding the timing analysis and get the bitstream files to be downloaded into the FPGA. So these are the steps involved in the IAR filters and FAR filter designs. Thank you.